Okay, Bismillah. Bismillah. Okay, we continue our discussion, our course, SMS 2310, okay, mathematical analysis. And for today, we will continue still in the topic of double integral, and will be the last topic on the double integral. And next week we will come to we will discuss a new topic on the triple integral. Okay, so we will end our topic double integral by today, and next week we will continue on triple integral. Okay, okay, I want to start. Let us recall something that you already discussed in the previous course about polar coordinates. Okay, so let's recall back what the meaning of polar coordinates. Okay, polar coordinates. If I'm not mistaken, all of you already discussed about the polar coordinates in the course of analytic geometry. So therefore, I just want to recall. I will not consider any example on polar coordinates. Okay, of course, polar coordinates it can be represented by this form. Okay, R and theta. Okay, so we have a such of coordinates that depend on R and theta. And of course, such of coordinates here we call it as a polar coordinates. Okay, now let us recall what the meaning of R and theta here. Okay, okay. Of course, we will have a such of well-known coordinates called Cartesian coordinate, or we can say Cartesian coordinates here as a rectangular coordinates. Okay, just the same thing. Okay, so I will have Cartesian coordinates, or such of Cartesian coordinate here we can call it as a rectangular coordinates. Okay, rectangular coordinates. Okay, the same thing. Okay, okay. Of course, such of Cartesian coordinate, okay, is a well known by all of you. We can represent such of Cartesian coordinates as the xy. Okay, xy. Okay, of course, we will consider such of Cartesian coordinate in the two-dimensional. Okay, in the two-dimensional, meaning that we have a such of coordinate here, x and y, where such of coordinate is taken from two-dimensional. Okay, R2. Okay, so this one. Okay, such of coordinate here is called Cartesian coordinates. Okay, and of course, when you draw this point, okay, when you draw this point in the xy plane, okay, so we have an xy plane here. Okay, and then we have a point xy. What do you mean of xy? X here will represent the unit, okay, along x-axis, and then this y will correspond the a unit, okay, along y-axis. Okay, for example, we have one point, okay, and that be such a point xy. Okay, so this one we call it as a Cartesian coordinates, or we can say also this one as a rectangular coordinates. Okay, why this one we call it as a rectangular coordinate? Because this x will represent the value, okay, value of unit along x-axis. For example, if I have the value x here, okay, so this will represent this value, this unit, and then this y here will correspond to this value. Okay, this one. Okay, so we have such of this y will correspond to this value, x will be correspond to this value, so we have something like rectangular. Okay, rectangular. Okay, of course, such of Cartesian coordinate here, I can consider it as a rectangular coordinates. Okay. 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 Of course, now our problem here now we want to recall back. Okay, we want to recall back. So how from this Cartesian coordinate, okay, we have a such of Cartesian coordinate, and then we want to change into polar coordinate. Okay, so given that a point, okay, rectangular coordinate, okay, Cartesian coordinate. So now we want to recall how from this Cartesian coordinate we can change into polar coordinate. Okay, meaning that polar coordinate we have a such of representation here, r and theta. Okay, and of course we need to understand. Okay, we need to recall back what the meaning of r and then what the meaning of theta. Okay. Okay, so now let's recall what the meaning of r and what the meaning of theta here. Okay, so firstly we have a point in the xy plane. Okay, then we have this point. Okay, let be x and y. Okay, and then such of xy, okay, a point here. So now we will draw. Okay, we will sketch. Okay, we will draw some. I can say that some imaginary circle. Okay, imaginary circle with at the such of circle here is a center at the origin. Okay, 0, 0. Okay, we consider such of circle center at 0, 0, and now we just consider that our point xy here in this circle. Okay, in this circle. So now we will have such of imaginary circle, okay, center at the origin, and of course such of point, Cartesian point here, okay, is in this circle. Okay, and we know such of point here. Okay, when we consider a circle here, of course this circle we have a radius. Okay, we have a radius, and of course this radius here will be same. Okay, will be same, right? Okay, because we consider a radius. Okay, since we have a circle, and then this circle we have a radius. Of course, when we consider the length, okay, the length from any point, okay, any point in the circle to the origin, they will have the same length. Okay, if we consider this length, okay, such of this length, and of course they have a same length. Okay, they have a same length, meaning that if I take any point, okay, if I take any point in the imaginary circle here, and I consider such of length that this point to the origin, they will have the same length. Okay, of course this length here we call it as a radius. Okay, we call it as a radius of the circle. So we will denote our r here as a radius of a circle. Okay, so meaning that our r here is correspond to the radius of our imaginary circle here, that center at the 0, 0. Okay, and therefore we can calculate our r here. So how we can calculate our r here? Okay, so our r here, okay, we can calculate our r here by taking the square root of x squared plus y squared. Okay, so this one. Of course, our x and y here is given. Okay, we have a such of value of x and such value of y. Okay, because we consider such of point here is a Cartesian coordinate. Okay, of course we can we will have the value of x and y, and therefore we can calculate the value of our r here, because r here, like I say, r here we consider this one as a radius of this circle. Okay, such of imaginary circle. Okay, r here. And of course, when we calculate the value of r, we can find the value of r from this Cartesian coordinate. We can also find the value of theta. How we can find the value of theta? So theta here is equals to inverse tangent, and then we will take y over x. Okay, so now we can calculate this one. Okay, of course we can find our r and we can find our theta. Okay, from the Cartesian coordinate. Okay, and of course always remember when talking about theta here. Okay, when you're talking about theta here will be in radian. Okay, always remember our theta here will be in radian. Okay, and of course such a value r and theta here. Okay, such a value of r and theta here. Since our x here can be from minus infinity to infinity, my y here can be from infinity minus infinity to infinity. But for the value of r and theta here, of course my r here is always non-negative. Okay, my r here is always non-negative, and we consider a theta here. Theta here is always taken from 0 until 2 pi. Okay, such a value. Okay, so now we have a different. Okay, when we consider x and y, x can be from minus infinity to infinity, y also can be from minus infinity to infinity. But when we change into polar coordinate r and theta, now our r here is only taking non-negative, and our theta here will consider from 0 until 2 pi. Okay, so this one. Okay. So meaning that if I consider such of r theta plane, okay, so if I consider such of r theta plane, okay, meaning that I will have r and theta, okay, and of course my r here is non-negative, meaning that r here will be from 0 until infinity. So we will don't have this part, okay, this part here we don't have. And then my theta here from 0 until 2 pi, meaning we have a 0, and then we will have something like 2 pi here. So now we don't have the below part, we don't have this part. Then we will have only such of region. Okay, such of region. So this one only. Okay, of course the upper part also we don't have. Okay, we don't have the upper part. Meaning that when we consider such of polar coordinate, okay, we consider such of polar coordinate. So the point, okay, the point only take this region, okay, this part only. Okay, we don't have a such of value in the upper, and also the below one, and also the left part. Okay, so different with the Cartesian coordinate, because when we consider Cartesian coordinate, we will consider the whole thing. Okay, we consider the whole thing of the plane, xy plane. But when it comes to the polar coordinate, we only consider some part. Here's some region here. Okay, this one. Okay. Okay, so now, so this is how we can change from the Cartesian coordinate to polar coordinate. Okay, meaning that from this xy we can find r theta by using this formula. Okay, now the next question, how we can change from the polar coordinate to Cartesian coordinate. Now we will have, if we given that polar coordinate, so now how we can change into Cartesian coordinate. Okay, meaning that if we have such of a point in the polar coordinate r and theta, so now how we can change into the Cartesian coordinate. The Cartesian coordinate here, of course, we have x and y here. Okay, we consider in the xy plane here. Okay, of course, this one you already discussed in the previous course, and then let's just recall. Okay, meaning that, so now how we can find the value of our x and y here. Okay, so meaning that my x here, okay, I can find by this formula. Okay, I have r cos theta, and of course this one I will have r sin theta. Okay, so this one. So this is how we can change from the polar coordinates into Cartesian coordinate. What the meaning of we want to change from polar coordinate to Cartesian coordinate? Meaning that if we have a such a point, okay, r and theta, we have the value of r and theta. Now we want to find the value of x and y. So how we can find the value of x and y? So given that this formula, r is equals to r cos theta, y is equals to r sin theta. R here we have this value, we just substitute this value, and theta here also we just substitute this value. Then we can find the value of our x and y. Okay, so this is how we can change from the polar coordinate into Cartesian coordinate. Okay, such a formula. Okay, if we have a Cartesian coordinate, we want to change to r theta. Then we will use the first formula where r here is equals to square root of x squared plus y squared, and then my theta here will be inverse. Okay, we take the inverse tangent here, y over x. Okay, by this formula. Okay, so this one is just inverse. Okay, of course, when you consider such of change here is a one-to-one. Okay, you have a one-to-one mapping here. Okay, one-to-one mapping here. What the meaning of one-to-one mapping here? Meaning that if you a point, okay, a polar one point polar coordinates here will correspond to only one point in the Cartesian coordinate. Okay, you cannot have a 2-point Cartesian coordinate correspond to 1-point polar coordinate. Okay, same thing. When you consider 1 point in the Cartesian coordinate, then you only have 1 point. Okay, it corresponds to 1 point in polar coordinate. Okay, it cannot be 2. Okay, you cannot have a such of 1 point in the Cartesian coordinate correspond to 2 point. Okay, it correspond to 2 point in the polar coordinate. So we don't have such of correspond. Okay, we don't have such of 2. Meaning that you only have one-to-one correspondent. Okay, one-to-one corresponding between the Cartesian coordinate and also polar coordinate. Okay, so this is the second thing. Okay, the second remark. Okay, when you want to change from Cartesian coordinate to polar coordinate, and when you want to change from polar coordinate into Cartesian coordinate. Okay. Okay, so today we want to discuss about double integral. Okay, double integral in polar coordinates. Okay, or such of double integral in polar coordinates here, I can consider it as a polar integral. Okay, it's just the same thing. Okay, polar integral. Okay, so today this will be the last topic in the double integral, and we want to discuss. Okay, we want to discuss about double integral in polar coordinates. Okay. Okay. So now, in previous class, we already discussed about the substitution method in double integral. Okay, of course, when you want to consider a substitution in the double integral, we will have such a formula. Okay, and then when we have a such a formula here, after that we just need to substitute all terms, okay, in this formula, and then we just evaluate, okay, this double integral. Okay, of course, when we consider substitution in double integral, okay, so we need to have 5 steps. Okay, first we need to know the formula, and then after we have a formula, then we need to do the 5 steps. Okay, we need to do the 5 steps. Okay, meaning that this 5 steps, after you do the 5 steps, then you can evaluate this double integral under some substitution, okay, or under some transformation, okay. And of course, why we consider the substitution in double integral, okay, such of substitution method here, just make sure that you will have the easy calculation, okay, easy calculation, okay. For example, we will consider a lot of example, and you already do a lot of exercise, and you see that when you have a such of R, okay, region R, that maybe have a difficulty to evaluate this function over this R, then under some transformation, and then you apply the formula, and then you find the whole thing, and then you just substitute in this formula, and then it makes your calculation become much easier, okay. You can evaluate this double integral, okay. Okay, so now let's try to understand, okay. Actually, when we consider a double integral in the polar coordinates, or we can call it as a polar integral, always remember that such of double integral in polar coordinates, actually we apply, okay, apply from the substitution in double integral, okay. We just apply the formula here, okay. Because of that, I just want to start with the substitution in double integral, so that you can see and you can understand, okay, where the double integrals in the polar coordinates, okay, come from, okay. Of course, the formula of the double integral in the polar coordinate, so we will have such a formula, but this formula actually is come from where, okay. So this is the question, okay. Just to make sure that you understand, actually double integral in the polar coordinates, okay, it actually comes from the substitution in the double integral, okay. And of course, when you consider the substitution in double integral, we will have these 5 steps, okay, 5 steps, okay. Let's first start, okay. Let's first start with the first one, okay. The first step, of course, we need to have the transformation, okay. Transformation here meaning that we need to substitute, okay. We need to change such of variables x and y into some function depend on 2 variables, okay. So of course, since we consider this one as a, since we can change, okay, from Cartesian coordinate to polar coordinates, and inverse also, we can change from polar coordinates into Cartesian coordinate. So we can consider such of transformation that x here is equals to r cos theta, and y here is equals to r sin theta, okay. We can consider such of transformation, okay. Such of transformation here, of course, because we call it as a polar, okay, polar coordinate substitution, okay, polar coordinate substitution, okay. So we have x equals to r cos theta, and y is equals to r sin theta, okay. Of course, our x here, we substitute into some function depend on 2 variables with r and theta, y also from function with 2 variables, which is r and theta, okay. And then the second thing, what is our second step here? We need to find the Jacobian, okay. We need to find the Jacobian, meaning that we need to find j r theta, okay, because now we have 2 variables which is r and theta, meaning that we need to find this Jacobian. So this one, by the definition, this one is equals to what, okay. This one you need to find the determinant, okay. Of course, the first element here will be what, okay, partial derivative with respect to partial derivative of x with respect to r, okay. So now dx dr, so dx dr here is equals to cos theta, okay. So this one will be dx d theta, dx d theta here is equals to minus r sin theta, okay. So what is the dy dr? Dy dr here is equals to sin theta, okay. What is the dy theta here? Dy d theta here will be r cos theta, okay. So we have such of Jacobian here. And when we find the determinant here, so you have r cos squared theta, okay, and then this one will have minus, so we'll have plus r sin squared theta, and of course this one cos squared theta sin squared theta plus is equals to 1, so therefore this one is equals to r. Okay, when you find the Jacobian here is equals to r. Okay, so this one. Okay, and then what is our third step? Okay, the third step here will be, okay, so we need to change, right, our function here fxy. Okay, so we need to change our fxy here into, so this one, so x here meaning that we have r cos theta, so meaning that we have r cos theta, and then this one y is equals to r sin theta. Okay, so we need to, the third step here, we need to change, okay, our function here in terms of x and y, and then we need to substitute our function here in terms of r and theta. Okay, of course my x here now is equals to r cos theta because we consider such of transformation, and y here is a r sin theta. Okay, and then of course the number 4, the fourth step here, meaning that we need to change the region of integration. Okay, we need to change our region of integration of r here into g. Okay, if you remember, the important thing here, we need to change such of region of integration of r. Okay, what do you mean of r here? R here is a region of integration in the xy plane. Okay, and of course under this transformation, meaning that we need to change into g. G here is what? G here become a new region of integration, but of course since our transformation here depend on r and theta, so now g here become a new region of integration in r theta plane. Okay, in r theta plane. So we have a region of integration in the xy plane, then we change into the region of under this transformation, we change into new region of integration in the r theta plane. Okay, so we have r theta plane here. Okay, and of course the fifth step. Okay, of course the fifth step here, we need just to substitute back into our formula. Okay, what is our formula? What is our formula previous class that we already discussed? So meaning that we will have r fxy dA. So this one is equals to what? This one will be equals to, okay, so now I will have new region of integration g. Okay, and of course I need to substitute this one f r cos theta r sin theta. Okay, and then we will have a Jacobian. Okay, always remember we have a modulus of our Jacobian. What is the modulus of our Jacobian here? Jacobian here we already calculate. This one is modulus of r. Okay, modulus of r. Since our r here is non-negative, so I can just take this one as equals to r, and then we'll have a dA. Now dA here should be depend on with respect to r and theta. Okay, we have a two variable r and theta here, so I can write this one as dr d theta. Okay, so this one. And of course, such of double integral here. Okay, this formula, such of double integral here. So this one, we can call it as a polar integral. Okay, polar integral. Okay, polar integral. So this one is just a polar integral. Or we can say that this one is just a double integral in polar coordinates. Okay, this is the formula of double integral in polar coordinates. Okay, of course, okay, I just want to repeat once again. When you consider a double integral in polar coordinates, okay, always remember, actually double integral in polar coordinates is just a substitution in double integral. Okay, meaning that you will evaluate such of double integral here under some substitution, okay, or I use the word some transformation. Okay, which transformation? Okay, of course we consider such of transformation here in polar coordinates. Okay, meaning that I will consider such of transformation that x equals to r cos theta, y is equal to r sin theta. Okay, and then of course we just use the formula of the substitution in double integral. Okay, we need to substitute the whole thing, meaning that we need to find the Jacobian, and then we need to substitute this one. Okay, this function here. Now I have a function here depend on r and theta, and of course we need to change the region of integration here from region integration from Cartesian coordinate, okay, into the new region of integration in the polar coordinates. Okay, I'm sorry, I forgot that word to mention. So this is the region of integration in Cartesian coordinate. Now we will have a new region of integration G in the polar coordinates. So now we have a G here in terms of r and theta. Okay, of course the fifth step, okay, we just substitute back, and then we will have such of form. Okay, we have a such of form. So this form actually is a double integral in polar coordinates. Okay, so this one. Okay. Okay. So let's just consider example. Okay, let's consider example. Okay, of course the formula here we can just memorize. Okay, we can just memorize the formula, meaning that we don't need to find the whole thing here. Okay, we don't need to check. We don't need to have this 5 step. Okay, but of course if you forgot to get this formula, then you need to start back. Okay, you need to consider the whole. You need to start first step, second step, the step until the 5th step. Okay. Okay, let's consider example. Example 1. So evaluate the integral okay, so I will have such an integral here, r e x squared plus y squared, and then I have a dE. Okay. Okay, so where r here is the unit disk. Unit disk in this xy plane. Okay, the xy plane. Centered at origin. Okay, at origin. Okay, at the origin. Okay, so this one. Okay. Okay, of course. Okay, so such of example. Okay, now we want to integrate such of double integral here. Okay, so where r here is the unit disk in the xy plane, centered at origin. Okay. Okay, so such of example here. Okay, we want to discuss. Okay, I will show you. Okay, how we can evaluate such of integral here by using the polar integral. Okay, polar integral. Okay, so how we can evaluate this double integral using the polar integral. Okay, of course, why we want to integrate such of integral here using a polar integral. Since, like I already mentioned just now, we just want to have a such of easy calculation. Okay, easy calculation. Okay, meaning that when we want to have a such of easy calculation, meaning that you need to apply the substitution method. Okay, substitution method. Okay, so now we have this one. Okay. Okay, of course, straightforward. Okay, straightforward. Okay, by the formula. Okay, R E x squared plus y squared dA. Okay, so therefore this one, by applying the formula here, okay, under the polar coordinate transformation, so therefore this one I can write this one is actually the double integral of G. Okay, and of course my x here I need to substitute into r cos theta. My y here is also I need to substitute into r sin theta. So I will have something like RE r squared, okay, cos squared theta, okay, and then plus r squared sin squared theta. Okay, because we consider the transformation polar coordinate. So my x here r squared cos squared theta, r cos theta, and my y here r sin theta. And always remember we have a Jacobian here, right? Okay, what is our Jacobian? Our Jacobian here will be r. Okay, we have r, and of course this one will have dr and d theta. Okay. Okay, if you remember the formula, so you can just substitute right away. Okay, but of course, if you forgot the formula, okay, formula of a polar integral, so I will suggest you to start. Okay, from first step, second step, third step, fourth step, and then the fifth step you just substitute. Okay, and if you already memorize the formula, you can just use it right away. Okay, so this one. Okay, of course, what the meaning of this one? R squared cos squared theta plus R squared sin squared theta here. So therefore, this one is just the R squared. Okay, so now I have R squared, and then I will have R dr d theta. Okay, so I will have this one. Okay, so now we will have a simple, okay, simple form here. And actually we can just, okay, we have a simple form, and of course this one will help us, okay, since we will have a easy calculation here. Okay, so now the important thing here, this part G. Okay, of course this G here we have a new region of integration in the polar coordinates. Okay, meaning that we will have r and theta here because we have with respect to dr, with respect to theta. Okay, first, of course, we need to sketch our r here. What is our r here? Okay, our r here, it mentioned that our r here is the unit disk. Okay, r here is the unit disk centered at the origin. Okay, so what the meaning of unit disk? Unit disk here meaning that we have a circle with radius 1. We have a circle with radius 1, so we have 1 minus 1 is centered at 0, 0. So I will have 1, and then I will have minus 1. So I will have, okay, this up. So this one will be my R. Okay, so this one will be my R. Okay. Okay, so now, of course now, we will have, okay, so now we will have such of G here, new region of integration here in the polar coordinate. Since I have R, since I will have dr and theta, d theta meaning that the first limit of integration here with respect to R, the second limit of integration here with respect to theta. So now I will have R and theta. Okay, So I will have r at theta. Okay, so meaning that we need to find, okay, what the limit of integration with respect to r, and then what the limit of integration with respect to theta. Okay, how to find the limit of integration with respect to r here? Okay, so now what is r? R is actually our radius. Okay, our radius here. Okay, of course, our radius here we need to take from origin. Okay, so from origin, so we have 0, 0. Since our r here cover the whole thing of our circle. Okay, it cover the whole thing of our circle. So meaning that it will start from 0, 0, and then will go out at this point. Okay, it will go out at this point. So it will start from this value, and then it will go out to this value. Okay, such a point here, okay, 0, 0. When my r here at the 0, 0, what is r 0, 0 here? So r 0, 0 here, meaning that my r here is equals to 0. And then it will go out to this point. Okay, this point will correspond to this. Okay, will correspond to this line. Okay, this line here. Okay, and since this line here, we will have the same radius. Okay, when you change your r here into some point here, some point here, some point here, it will give you the same. Okay, it will give you the same value of r. So what is the value of r at this point here? So since this one is just the radius of our circle, the radius of our circle here is r equals to 1. So now I will have r is equals to 1. Okay. Okay, so now the limit of integration here with respect to r from 0 until 1. How about theta? Okay, how to get the value of theta here? In the polar coordinates, we always start from this axis, right? Okay, this axis here, axis and this axis. Okay, meaning that our theta here will be equals to 0 because our r here, the whole thing here, okay, inside of this circle. And then we need to rotate, right? Okay, we need to rotate counterclockwise. Okay, counterclockwise. Since my r here is cover the whole thing of our circle, so it will start from this theta equals to 0, and then it will rotate the whole thing. Okay, it will rotate the whole thing here. So meaning that my theta here will be from 0 until 2 pi. Okay, so this one 2 pi. Yes. So this is how you find the limit, okay, for the r, and also the limit of theta. Oh, sorry, this one should be theta. Okay, so this one should be theta. Okay, and of course, when we have the limit of with respect to r, we limit with respect to theta. So we can just evaluate lah. Okay, we can just evaluate this double integral. Okay, so now with respect to dr, so I have a r e r squared r here, meaning that this one is equals to 1 over 2 e r squared. Okay, my r here from 0 until 1. Okay, my r here from 0 until 1, and then my theta here from 0 until 2 pi. Okay, and then I will have okay, so I will have d theta. Okay, so I will substitute this one. When I substitute, I will have 1 over 2. Since this one is just a constant, right? Constant, I can just put outside. Okay, so now 1 over 2. Okay, 1 over 2e. Okay, so I will have e. Okay, I will have e, and then when r here equals to 0, e power 0 equals to 1. So I will have minus 1. Okay, of course my theta here from 0 until 2 pi, and then I will have d theta. Okay, so since I don't have theta here with respect to d theta, so this one 1 over 2 e minus 1, and then I will have theta here from 0 until 2 pi. So in the end we will have pi e minus 1. Okay, so this one will be the answer. Okay, so this one will be the answer. Okay, let's consider example number 2. Okay, example number 2. Okay, now let's evaluate this integral. Okay, 2xy dA. Okay, where R here, okay, is the region. Between, okay, between the circles, okay, between the circles of radius 2 and radius 5, okay, in the center, okay, center and the origin, okay, in the xy plane, and lies, okay, and lies in the first quadrant. Okay, so this one. Okay, let's consider this second example. Okay, such a second example. Okay, and I want to show you from this second example, it's easy to calculate such of integral here using polar integral. Okay, using polar integral. Okay, so okay, let's solve this second example. Okay, let's write the first. Okay, the first thing always, okay, we just write the formula. Okay, the formula. So now I will have R, okay, and then I will have 2xy, okay, and then have dE. Okay, so this one. Okay, and then I want to show you this second example. We can solve easily by using the polar integral. Okay, so meaning that this one, now I will have G. Okay, let me G first. Okay, so I have 2xy. Okay, meaning that I need to change this one into polar coordinates. Okay, R and theta. So now I will have 2. Okay, what is my x here? My x here will be R cos theta. And then what will be my y here? My y here will be R sin theta. Okay, and of course, now I will need to times with Jacobian. Okay, I need to times with Jacobian. So what is my Jacobian here? My Jacobian here is R. Yes, I will have R. And of course, since my term here in terms of R and theta, now we will have dr d theta. Okay, so it's fine. Okay, it's easy to remember the formula. Okay, so meaning that you can see when we consider polar integral, now my dA here is R dr d theta. Okay, dA R dr d theta. Okay, always common mistake. Okay, common mistake that done by the students. Okay, when they want to evaluate such a double integral here in polar integral. Okay, they always forgot to put r here. Okay, meaning that they will take dA here is equals to dr d theta without r. Okay, without r. So meaning that if you write such a formula here without r here, meaning that your dA here you just write as dr d theta. So of course your calculation here is wrong. Okay, your calculation here is wrong. Because of what? Because when you are not consider r here, meaning that you don't have a Jacobian here. When you don't have a Jacobian here, so such of substitution in double integral here is wrong. Okay, because we always discuss when you consider the substitution in double integral here, the formula here they have a Jacobian. Okay, and without Jacobian, so your calculation is wrong. Okay, always remember this dA is equals to r dr d theta. Don't forget to put your r here. Okay, and of course r here we need to times all the function of fr theta here. Okay, okay, now let's evaluate this one. Okay, so now our next step is we need to find the limit of integration, okay, of g here. So meaning that since I have dr d theta, the first limit of integration here of course with respect to r, okay, because dr, so r, and then the second one d theta, so this one should be theta. Okay, first limit of integration with respect to r, and the second limit of integration with respect to theta. Okay, okay, what is our r here? Okay, mention that my r here, okay, you mentioned that my r here is what? R here is the region between these two circles, okay, with radius 2 and radius 5, and of course center at the origin, meaning that I will have first circle with radius 2, and then the second circle with radius 5. Okay, so I have this one. Okay, then my r here will be in between. My r here will be in between, so meaning that my r here will be in between here. Okay, so this one is my r. Okay, so I have something like what? Ring, right? So I have something like ring. Okay, ring. Super ring. Okay, super ring. Super ring. Okay lah, ring. We have something like ring here. Okay. Okay, so now, okay, now our next problem, our next step, we want to find the limit of integration with respect to r and with respect to theta. Okay, first, let's consider r here. How to find the limit of integration with respect to r here? Meaning that I need to take my r here from the origin, okay, and then just, okay, go to something like this direction. Okay, that be something like this direction here. Okay, of course, since my r here, okay, it only cover the between part here, right? This part only. Okay, so meaning that my r here will not start from 0, 0. Because of what? Because my region here doesn't have, my r here doesn't have this part. Okay, this one is not our r. So meaning that my r here will start from this one. Okay, and then we'll go up from this one. Okay, and of course, if I consider my length here, okay, my length here along this line, okay, I consider such of length here along this line, okay, it will have the same length. Okay, you see, it will have the same length here. So this length will give me what? What the length of this one? So this one will be r is equals to 2. Okay, and then of course it will go out to this point here. Okay, and of course if I consider the length, okay, the length along this line, okay, the length along this line, that outside here, it will have the same length. Okay, it will have the same length. What the length of the what the length of this? Okay, this one. So this one is just the radius, right? The radius of my circle of radius 5. So meaning that r here is equals to 5. So therefore I have r here is equals to 5. Okay, my r here from 2 until 5. Okay, and then how about my theta here? My theta here will be start from this one, right? Okay, my theta here will start from this one. Okay, and then it will rotate. Okay, so it will rotate all region of my R here. Okay, so it will rotate. So you see my R here will cover the whole part here. Okay, the whole rotation here until it end to this one. Okay, of course my theta here is starting from 0 until 2 pi. So 0 here until 2 pi. Okay, so this one. Okay, so after that, okay, we just can evaluate this one. Okay, we can just evaluate easily. Okay, so therefore this one I can write this one as what? So this one I can write as theta is equals to 0, theta equals to 2 pi, r equals to 0, r equals to 5. So I will have r power of 3. Okay, now I have cosine. Okay, I have 2. Okay, so I will have something like 2 cos theta sin theta. So therefore I can write this one as sine 2 theta. Okay, and then I have dr d theta. Okay, so this one. So we have a simple, okay, simple representation here. Okay, simple form here. Then you can just evaluate this double integral. Okay, okay, let me this one is your exercise. Okay, you can do by yourself to integrate this one. Okay. Okay, let's consider the third example. Okay, you just can finish this calculation. Okay, let me this one is your exercise. Okay. Okay, example number 3. Okay, determine the volume determine the volume of the region that lies under sphere, under the sphere. Okay, under the sphere, x squared plus y squared plus x squared equals to 9. Okay, above the plane. Okay, above the plane z equals to 0. Okay, with the plane z equals to 0. Oh, sorry. Actually, I do a mistake in the example 2. Okay, I forgot about it in the first quadrant, right? Okay, in the first quadrant. Okay, sorry. Okay, it's okay. Okay. Okay, I will repeat. I will repeat again the example number 2. Okay, I will repeat again the example number 2. I have a mistake. Consider the theta. Okay, consider theta because I forgot that our question in the first quadrant. Okay, in the first quadrant, it's okay. I will repeat. I will repeat once again. Okay, I will repeat once again. Okay, let's consider the third example first. Okay, above the plane z equals to 0. Okay, and inside Okay, and inside x squared plus y squared is equals to 5. Okay, inside cylinder. Okay, inside the cylinder. Okay, inside the cylinder. Okay, x squared plus y squared is equals to 5. Okay, this one. Okay, determine the volume of the region that lies under the sphere. Okay, x squared plus y squared plus z squared equals to 9. Okay, above the plane, z equals to 0, and inside the cylinder, x squared plus y squared is equals to 5. Okay, and of course, always remember when consider the plane z equals to 0. What the meaning of z equals to 0 here? Meaning that z equals to 0 here is just a xy plane. Okay, the same thing. When you consider the xy plane, what the meaning of xy plane? Xy plane meaning that it's just a z equals to 0. Okay, so we have this one, and then we have xy plane. So this one. Okay, so now we want to find the volume. Okay, the volume of the region that lies under the sphere. Okay, so we have this sphere, meaning that we need to find the volume under the graph. Okay, in between, inside of this sphere, and then above z equals to 0, xy plane, and then of course inside the cylinder. Okay, inside the cylinder of x squared plus y squared is equals to 5. Okay, so if we try to see, okay, where is this region here? Okay, where is the volume we want to find in this region here? Okay, so meaning that we will have a sphere z y. Okay, we have a sphere. Okay, so meaning that we will have a sphere here. Okay, we have a sphere, and then we radius 9. Okay, our sphere here, our sphere here is not the radius 9, but we have a x squared plus y squared plus z squared is equals to 9, meaning that we have a sphere with radius 3. Okay, we have a radius with radius 3, so we have minus 3. So I will have 3 minus 3, then I will have 3 here, and then I will have minus 3 here. Okay, so this one. Okay, and then it say that our R here, our region that we need to find the volume here lies under the sphere. Okay, under this sphere here. Okay, meaning that it will be under this sphere. Okay, and then above z equals to 0. So z equals to 0 meaning that we will have this one. So we are not consider at the below part. Okay, we will not consider sphere at the below part. Okay, we only consider sphere at the upper part here. Okay, because what is one? Okay, hemisphere. We consider the hemisphere upper part here. And then inside the cylinder, inside the cylinder, x squared plus y squared is equals to 5. Okay, meaning that we have a at the z equals to 0, we will have a circle with radius square root 5. Okay, we will have a circle with radius 5, and of course inside cylinder meaning that we need to consider inside of the circle, and of course then this one will be, okay, so this one will be our R. Okay, so this one will be our R. So this one is not will be our R, this one will be our region. Okay, our region that we want to find the volume here. Okay, our region that we need to find the volume. Okay, we need to find the volume of this region. Okay, we need to find the volume of this region. Okay, this one. Okay, on this part here. Okay, so this one. We are not talking about the whole part of the hemisphere. Only some part here. Okay, only some part of this hemisphere. Okay. Okay, of course, how to find the volume of this region? Okay, how to find the volume of this region? Okay, so now we already know that to find the volume here, meaning that we need to integrate function with two variables here. Okay, meaning that we'll have fxy, okay, and then I will have dA, and then I will have r here, okay, this one. Okay, of course, what is our fxy here? Okay, so since the upper, okay, the graph here, graph of our surface at the upper part here. So therefore, since I have a x squared plus y squared plus z squared is equals to 9, so therefore I need to find the function of my z here. Okay, so this one I can consider this one as equals to z. So meaning that I will have z here is equals to square root of 9 minus x squared minus y squared. Okay, why we consider that z here is equals to square root of 9 minus x squared minus y squared? Because we consider the upper, okay, upper part of hemisphere, okay, upper hemisphere. And of course, if we consider the below part of hemisphere, okay, then I will have z equals to minus, okay, minus square root of 9 minus x squared minus y squared, okay. And then of course this one, I can write this one as well. So this one, to find the volume here, I have r, and then I will have 9 minus x squared minus y squared, and then I will have dA. Okay, so this one. So this is how we can find the volume of our region here that lies under this sphere, and then above this one. Okay, so for this case, it's easy to us to evaluate such of integral here in the polar, okay, polar form. Okay, so meaning that I will have, so this one I will have G. Okay, new region of integration in the polar coordinates. Okay, now I will have square root of 9. X here I can substitute into r cos theta, so I will have minus r squared cos squared theta, and then r here I can substitute into r sin theta, so minus r squared sin squared theta, so I will have minus r squared cos squared theta minus r squared sin squared theta. I can just factor the minus r squared, and then I will have cos squared theta plus sin squared theta, so therefore I will have 9 r squared. Okay, you can check. You substitute r cos theta, you can substitute r sin theta. You only have 9 minus r squared. And of course, this dA. Why is dA here? Since I want to evaluate this integral in a polar form, dA here will give me r dr d theta. Okay, so this one. Okay. Okay, so now we need to find the limit of integration of g here, since I have dr and theta here. So first limit of integration here should be with respect to r, and then the second limit of integration here with respect to theta. Okay, so meaning that I need to find the limit with respect to r, and then I need to find the limit with respect to theta. Okay, first let's sketch my r here, the region of integration here. What is my region of integration here? My region of integration here will give us a circle, right? Okay, circle with radius square root 5. Okay, circle with radius square root 5. Okay, so I have minus square root 5. Okay, and of course my r here will cover the whole thing, right? Because they say that inside of this cylinder, meaning that I will cover the whole thing here, r here. Okay, so this one will be my r. Okay, now how to find the first limit of integration of r here? R here meaning that I need to start from the origin, and then I will go to this direction. Okay, and then it will go out to this direction here. Okay, and of course you see the line here. If I rotate, okay, if I rotate my length here, okay, my length here, I will do some rotation here. Okay, along this r here, it will give me the same length. Okay, it will give me the same length. Okay, since this one is just the radius of this circle, so of course my r here should be starting from 0 until square root of 5. Okay, argue from 0 until square root of 5. Okay, how to find the value of my theta here? Okay, so my theta here should be starting from this one. Okay, and then it will rotate. It will rotate along my arc. Okay, it will rotate, it will rotate, it will rotate, and then it will end to this one. Okay, because my r here cover the whole thing, right? So meaning that my theta here starting from 0 until 2 pi. Okay, 0 until 2 pi. Okay, so now I have some simple form here. Okay, simple representation here. So I just leave it for you to calculate. Okay, to finish this one. Okay, let me this one is your practice. Okay. Okay. Okay, before I give you a home task. Okay. Okay, I just want to repeat again the second example. Okay, I forgot that the second example mentioned about the first quadrant. Okay, the first quadrant. Okay. So meaning that, okay, the previous thing I have what? I have what? Okay, okay, so if I'm not mistaken, I have this one. If I'm not mistaken, I have R3, okay, sine 2 theta, and then I will have dr d theta, right? Okay, so this one. Okay, okay, and of course my r, okay, I made some mistake before. So my y and then x. Okay, so I have this r, right? Okay, so r here in between these two circles. Okay, the circle with radius 2 and the circle with radius 5. Okay, so since my r here say that the region between the circle of radius 2 and radius 5, center at the origin, that lies in the first quadrant. Okay, the first quadrant meaning that this part only. Sorry, I forgot this one. Okay, only this one. The first quadrant only. Okay, so meaning that this one is my R. Okay, not the whole thing, but only the first quadrant. Because the question say the first quadrant. Okay, I forgot about this part. Okay, I forgot about this part. Okay. Okay, of course my R here should be started from origin, right? From origin, and then you go to this one. So it will come to this point first, and then it will go up to this point. And of course, if I consider this length, okay, when this length is moved around my R here, okay, it will give me the same length. Okay, since my R only this part, so you can see the length here is just the same, because this one is just the radius of 2, right? Okay, so of course my R here is equals to 2, and then if I consider this length, okay, since my length here is moved around R here with same length, okay, with same length, R here is equals to 5. Okay, but now my theta, okay, my theta here, it will start from here, right? Okay, and then it will rotate. It will rotate along my R. Okay, along my R. Okay, along my R. But then it will stop at this point. Okay, my theta here from this one, and then it rotate along R. But since my R here only in the first quadrant, okay, my R here in only first quadrant, it will stop at this point. Okay, meaning that it's not rotate the whole thing. Okay, because my R here only in the first quadrant. So my theta here will be start from here. Okay, theta here is equals to 0 until theta is equals to pi over 2. Okay, theta here equals to pi over 2. Okay, because you need to take the angle here. Okay, the angle here. So theta here from 0 until theta equals to pi over 2. Okay, sorry. Previous one is wrong. Okay, because I forgot about the first quadrant. Okay, I just take the whole thing here, right? Okay, actually the previous one is wrong. So this one should be the correct one. Okay, so my theta here from 0 until pi over 2. Why? Because my R here only considered in the first quadrant. Okay, in the first quadrant. Okay, okay, so you can finish this calculation. Okay, finish this calculation. Okay, so before we end our class today, I give you home task. Okay, you can do by yourself. Okay, let be this one is additional example. Okay, home task number 1. So evaluate. Okay, this is an integral r. Okay, y squared plus 3x dA. Okay, dA. Okay, where r here is the region. Okay, is the region. Is the region in the xy plane. In the xy plane, and lies, okay, and lies between, okay, between x squared plus y squared is equals to 1 and x squared plus y squared is equals to 9. Okay, and okay, R is the region in the xy plane and lies between x squared plus y squared equals to 1 and x squared plus y squared equals to 9. Okay, at the third quadrant. Okay, and the third. Okay, so this was some task. Okay, of course, you see, you need to find. Okay, of course, this home task here, I ask you to evaluate such of integral here using the polar integral. Okay, when you have a polar integral, meaning that you need to find the limit of r and also the limit of theta. Okay, try yourself to find. Okay, try to yourself to understand. Okay, how to find the limit of r and also the limit of theta here. Okay, this one. Okay, first home task. Okay, the second home task. Determine the volume of region that below z is equals to 2x squared plus 2y squared and above the xy plane. Okay, what the meaning the xy plane here? Xy plane here meaning that x and z equals to 0 lah. Okay, inside above the xy plane, inside, okay, the cylinder. X squared plus y squared is equals to 16. Okay, so this one. Okay, second home task. Okay, you can try yourself. Okay, try to understand. Okay, and then try to complete the calculation previously. Okay, so that be these two home tasks will be your additional. Okay, additional example for today class. Okay, meaning that if you do these two home tasks, okay, then you will have a 5 example today. Okay, 5 example today. Okay, try this. Okay, so I stop at this part. Okay, next week we will consider a triple integral. Okay, a triple integral. Okay, so I will stop this topic. Okay, for the double integral part. Okay, and then I will see you next week. Okay, okay, so